Hello, chemists, and welcome to this episode of Crowded Beaker. Today, we're talking about half-lives, and we're not going to do any problems in this video. This is more of an overview video to show you how you might end up solving those problems, and we'll get to the problems in probably a later video. But in the meantime, let's talk about the theory of half-lives and so on. And I've produced a graph, just a general graph. It's theoretical for a first-order reaction. And most people, when I ask them about half-lives for the first time, have maybe heard about half-lives before, and maybe in terms of like radioactive decay, they think about carbon dating in their Earth systems class or biology class, or some other application like that. And that is true. It's a good way for us to start learning about half-lives. And half-life, let's start with the definition. So if you want to write this down, great. The half-life is the time. It's actually a length of time it takes for half of your original sample to decay or half your original sample to react. So you'll be left with half of the original sample. So the half-life is the time it takes for that to happen. And for a radioactive decay reaction that you may have studied before, the half-life is constant. Okay, so and I purposely made this half-life to be 2 hours all the way across. So for this reaction, because it's first order, and we have a half-life of 2 hours. Now, because it's first order, the rate of reaction is proportional to how much is actually there at that moment. So after half of it is gone, we're down to half of our original sample, and therefore we're at half the rate. So from here to the second, so the rate is slowing down, and so the time it takes to get from that to the next halfway amount down to 0.25 is actually going to be the same as the time it took to go from 1 to 0.5 because the rate is slowing, and it slows proportional to how much is there. Then in another 2 hours, we've gone down to 0.125 and 0.0625 and so on and so on and so on. So for a first order reaction, the rate is the half-life. T1 half is the symbol we use for that. So T1 half is constant over time. So if you ever hear that, say an isotope has a half-life of 37.2 minutes, that's going to be constant regardless of how many atoms of that isotope you actually have in front of you, or the molarity of your first order ingredient in your reaction. And there's an equation for that, to calculate half-life, and that is the half-life of a first order reaction is equal to the natural log of 2, and that works out because the start is twice as big as the end. That's how the math works, divided by the rate constant. So as the rate constant changes, your half-life will change as well. But there's a quick little formula for that. You might also see it as written as 0.693 over K. 0.693 is the natural log of 2. Okay, so you can also say things like after the first half-life, we're down to half. After 2 half-lives, we're down to a quarter. After 3 half-lives, we're down to an eighth, and on and on and on. Now, theoretically, you would never get to 0. This is kind of a paradox. You will never get to 0 theoretically because you could always take half of whatever you have. But in actuality, you can get to 0 because when you're counting things like atoms, you get to this limit where you actually might have 1 atom left. And if that one goes, you are at 0. So you might have 8 atoms, then 4 atoms, then 2 atoms, then 1 atom, and then finally it's gone. So in practicality, you can get to 0. Theoretically, no, you would always have something, half of whatever is left there. Now, I don't know if you're aware. You may have learned about half-lives being constant over time for different things. I don't know if you're aware, but actually half-lives are not always constant. All right, and I'm sorry to be the guy that messes that up for you, but here we go. Let's talk about a zero-order reaction first. While half-lives are constant for first-order reactions, they are not for zero-order reactions, because zero-order reactions have a constant rate regardless of how much you have there. Now imagine I start with my 1 mole per liter, and after 2 hours, I'm down to half. Great, same as the other one. But this rate just keeps trucking along. It's not slowing down. And so half-life is gone, and then after another 2 hours, we're actually gone. We're done. We've used up all of our stuff. And if you look at it, the time it took to go from 1 to 0.5 was 2 hours. But from 0.5 to 0.25, it only took me 1 hour, half of that amount of time. And to go from 0.25 to 0.125 is only a half an hour, and then a quarter an hour, and so on. And it would just get smaller and smaller and smaller until I hit 0. So for zero order reactions, the half-life gets smaller over time. And it depends on how much you have at the beginning. So in our equation here, you have an A0. A0 is whatever your concentration is the moment you start measuring the half-life. From that point on, how long does it take? So A0 divided by 2K, and as A0 drops, your half-life is going to drop as well because it's proportional. And so that equation you might see in different charts of kinetics equations. And so be aware that that one exists. And if you ever see a problem that says successive half-lives are 20 minutes, then 10 minutes, then 5 minutes, and they're getting shorter, you know it's probably a zero order reaction. All right, let's contrast that with a second order reaction. Now, a second order reaction depends on the square of how much stuff you have. Excuse me. And therefore, as the concentration drops, the graph flattens out more over time. And so it might take 2 hours to get down to half, but now we only have half, but that's in a squared situation. So actually the half-life, the time it takes to get to half of that, is actually double what the original was. So the half-life went from 2 hours, now it's a 4-hour half-life, and from there on the rate has gotten so slow that it might take 8 hours to get to the next halfway amount. And so the T1 half gets larger over time for a second order reaction. And there's an equation for that. These are derived using the integrated rate laws. T1 half equals 1 over the constant. The rate constant appears in all of them, times the original amount at the time you start measuring that half-life, that amount. And so that equation will exist. You can also use the integrated rate laws to calculate half-lives, and I want to demonstrate that in a future video. But for today, for generally speaking and theoretically speaking, I wanted to get these